In the last few lessons, we've been applying some transformations to a particular function to create a new function. Today, what we'll be doing is actually determining transformations. Now, what does that mean? That means that basically we'll get given a function, get given a resulting function, and try to work out what transformations would have been applied to the original function here, for example, y equals x squared, to take it to the graph of y equals x squared plus 2. Now, this one's pretty easy to do by inspection or by looking at it, because you can just see that this is a translation 2 units up. So we would say that the y equals x squared graph was translated 2 units up to create this one here, y equals x squared plus 2. Now in this exercise, the transformations we find are only one possible answer. And in fact, there are infinitely many choices, and I'll try to explain to you how you can check whether your transformations work, because they may look different from the back of the book. So let's do this one here. Find a sequence of transformations which takes the graph of y equals x squared to the graph of y equals that. Now again, this is fairly easy to do via inspection, and I can see here that this negative sign means that the graph of y equals x squared was reflected in the x-axis. So I can see that. This 2 means we have a dilation factor 2 from the x-axis. This is a translation. 1 unit right. And finally what we've got is a translation 3 units up. Now you might ask, how did I know to state the transformations in this order? Now we'll talk about this on a fairly consistent basis after this lesson, but if we've got this as what we call a single x, what we can do is apply Dr. T or RDT to state the transformations. That is, we can read the transformations in the order of dilations, reflections and translations, or reflections, dilations and translations. But we can only use this if we've got the function with what we call a single x, that is x with a coefficient of +1. More on that later. So I think these are the transformations that take this graph here to this graph here. What if you're not so sure? Alright, well here's the process that we use to get the transformations to us, and we can do this for any function, starting with a function going to another function. So we're going to go from y equals x squared to y equals -2 x take 1 all squared plus 3. So we're going from this function to this function here. Now this was the original, this was the image, so we're going to put our images in here. And what we've got to do is do what I call get these ready to be paired up. Now what we'll do first of all with this equation on the right hand side here is go y dash take away 3 over -2 equals x dash take 1 all squared. Now what you'll notice here is that I've subtracted 3 from both sides and divided by -2. Now why did I do that? Well, what this would be is once I'd actually done the mapping from these transformations, this is what we would have subbed in to make a new function, and then we would have solved for y dash to create it. Okay, so essentially I'm going backwards to the phase that we were getting at from the last couple of lessons. Now that we've got these paired up, what I can do is just pair them up like this. I'm going to say that y is y dash take 3 on -2. And x is this thing here. X is x dash take 1. Alright, so now what we need is we need to get the transformations. Now, historically we've been solving for y and x, and it looks like these are already solved. But actually, if we want to state the transformations, recall that we go x comma y maps to a set of transformations to the x's and the y's to create our images. So in this case, what we need to get is the things that create the image. The things that create the image. And what the things are that create the image will tell, how can I say this? What we need is to get x dash by itself and y dash by itself so we can fill in the transformations in here. Alright, so I'm going to solve for y dash, which is negative 2y plus 3 equals y dash. And I'm going to write that in here. Negative 2y plus 3. Over here, we've got x dash equals x plus 1. So I'm going to fill in x plus 1 is x dash. Now what we can do is once we've got the mapping written out like this, we can simply read off the transformations. Now this is a translation, 1 unit right, and that's this one here. Alright, over to the y's. Now what we can do is we see this negative sign here and we can say that that's a reflection, or we could also say that we dilate by a factor of 2 from the x-axis. So I'm going to say reflected in the x-axis. This 2 will be dilation factor 2 from x-axis, and finally translation 3 units up. Alright, now the first thing you'll note is that you can put these transformations separately. So you can list the transformations of this x here and the transformations of this y here in 2 separate lots. And I know that that will seem like there's a different order to these transformations, but in fact this order here will produce the same set or the same transformations as this set here. Okay, and again goes back to the idea that the transformations can be stated in infinitely many ways. So these are correct and these are correct. Alright, let's go with the next one. State a possible sequence of transformations which takes the graph of 1 on x squared to this graph here. Now this is where it gets particularly difficult to do it by intuition or by sight, and in fact I can't do it at this point. So I need the mapping to serve up the transformations to us, and I've tried to work out different ways of doing it using function, but I always come back to doing mapping on these particular questions. So I highly recommend you do the same. We're going from y equals 1 on x squared to y equals 5 on 2 take x all squared. Alright, so again, this is the original, this is the image. So we're going to put our dashes onto the image. Now what we're going to do is get these ready for pairing. Now this has to have a 1 to match up with this. So what I'm going to do is divide both sides by 5. Y dash on 5 equals 1 on 2 take x dash all squared. Alrighty, now these are ready for pairing. So what I'm going to do is pair up those. Y is y dash on 5 and x is 2 take away x dash. Alrighty, so now what do I solve for? So what I'm going to do is again remind you that the mapping would look like this. Stuff done to x, stuff done to y to create x dash and y dash. Alright, so what I need to do is solve for x dash and y dash to put that stuff in here. So I'm going to go 5y equals y dash, and that's going to be 5y. This one is going to be x take 2 over negative 1 equals x dash. Now we can probably write that a little better by dividing through by this negative. So I'm going to write that as negative x plus 2 equals x dash. So dividing that by negative 1 and dividing this by negative 1. And then I'm going to write that in. Okay, so let's go and run or write down what these transformations are. So remember, I usually start with x and write those transformations. So starting with x, I can see the first thing that was done to x was it was negated. So we write that as a reflection in the y-axis. This means we've been translated to units. Right. Over here, we've got y being multiplied by 5. So we're going to say that this is a dilation factor 5 from x-axis. Alright, so now let's see how we would try this out. So I'm going to go and open up GeoGebra here, and I'll show you how you can test your transformations with GeoGebra and check it out. So the first thing I'm going to do is write f of x, or have a look at f of x equals 1 over x squared. Now I'm going to write this function here. So I'm going to call that g of x equals 5 over 2 take x all squared. There it is there. Alright, so the red function is what the green function becomes after running these transformations. Alright, so I'm going to quickly try and do this via functions. So I'm going to say that g of x can be found by doing, so reflection in the y-axis. This one here, if I want to reflect in the y-axis, remember what I do to f of x is I drop in that. Translated 2 units to the right means what I would do is put in x take 2 wherever I see an x. Right, so I'm going to rub out that and replace x with x take 2. So wherever I see an x, I replace it with x take 2. And then we've got a dilation factor 5 from the x-axis, so that just goes out the front there. Now, if my transformations work, if I type this in, so I'm going to say that g, what function? I've got h of x is equal to 5 times f of negative x take 2. And what happens is you can see that h of x, all right, is the same as g of x, which means when I apply the transformations to f of x, 1 on x squared, what happens is it does indeed produce this red graph here. Okay, so when I transform this green one using these transformations, it produces the red graph or the blue graph here. All right, which is exactly what I want. So I know that these 3 transformations work perfectly. They are correct. So the back of the book might have a different set of 3. That's fine. Okay, you've got to check whether yours have worked. All right, let's do this one here. So what we've got is a sequence which takes this to this. So we start with, so we're going to go from y equals 3 on x take 1 all squared plus 6 to y equals 1 on x squared. So this one here, the second function, is our image. So we're going from this back to this. So this one's not ready for pairing yet. I'm going to go y take 6 over 3 equals 1 over x take 1 all squared, and we're going to this. Right, so now I'm going to pair up the y dash with this. Y take 6 on 3 equals y dash, and x take 1 equals x dash. So that with that. Alright, now what we've been doing is just writing out the mapping. So this tells us we need to solve for x dash and for y dash. So I can see here the nature of these problems when I go from what I call a complicated function to a basic function will already create a algebraic sort of solution, I suppose, where y dash and x dash are the subject. So we can just throw them straight in. So this is x take 1, y take 6. Ooh, now hang on a sec. What I might do is rewrite this as y on 3 take away, now 6 divided by 3 is 2 equals y dash, and I'm going to write it in like that. Alright, now what I can do, that should be x take 1 there. Alright, so what I can do is read off the transformation. So I can see here that this is a translation, 1 unit left. This is y being multiplied by a third. So this is a dilation factor 1/3 from y, from x rather. And this one here would be a translation 2 units down. Now again, how do I know that the translation comes after the dilation? Well, I can see that what happened is we start with x, start with y gets multiplied by 1/3 and then has 2 subtracted from it. So I just read off in order that the expression is built up. Now, you might sort of go, all right, well, what if you didn't make this algebraic move? What would be the transformations then? Well, then the transformations would be to move 6 units down and dilate by a factor of 1/3, all right, which will produce exactly the same transformation as these ones here. It'll take that to that, okay? All right, so there are our transformations. All right, let's go with this one here. All right, so for this next one, we're going to state the transformations that map y equals root x to this really complicated looking thing here. And again, I've got really no chance to do this by kind of inspection. I need the mapping to help me here. So I'm going to go from y equals root x to y equals negative Now, this is the original, this is the image, so let's put the image notation in. Now what we'll do is we'll get ready to pair these up. So I need to get rid of this negative sign and I need to get rid of this +2. So I'm going to go y dash take away 2 over -1 equals root negative 5x dash take 3 over 4. Now, one more thing that I'm going to do, so I could pair these up that'd be quite okay right now. But what I'll do is I'm going to root the numerator and the denominator. So what I'm going to get is square root negative 5x dash take 3 over 2 equals y dash take 2 over -1. Then I'm going to multiply by this 2 here. So I'm only left with a numerator here. Didn't have to do this move. You would have got a different set of transformations if you'd left it like that and paired them up straight away. But I've decided to do it this way. So I've got 2 y dash take away 4 over -1 equals root negative 5x dash take 3. Alright, so I'm going to go them match with them. So I've got y equals 2 y dash take 4 over -1. And I've got x, this x here is this, negative 5x dash take 3. Alright, so again, what do I make the subject? Well, x comma y maps to this stuff here done to this x and this y here will produce the images. So I want to know what that stuff is. So I need to solve for x dash and y dash. So I've got negative y plus 4 on 2 equals y dash. And I'm just going to rewrite this as negative y on 2 plus 2 equals y dash. So I'm just going to make an algebraic move there, divide the y by the 2, the 4 by the 2. And I'm going to fill that in. So that's negative y on 2 plus 2. Alright, now the x's. So what I'm going to do is solve for x dash. The way I'm going to do that is negative x plus 3 all on 5 equals x dash. Now in this one here, what I did was I divided both of them by 2. This time I'm not going to divide both of them by 5 because, well, I don't feel like it. So I just want to do this a little bit differently, but again show you that I'm going to get a transformation that works. So this is negative x plus 3 on 5. Alright, now it's time to read off the transformation. So let's start with x over here and note that it gets negated first of all. So this is a reflection in the y-axis. Then it gets translated 3 units to the right. 3 units right. Then we dilate it by a factor of 1/5 from y. Okay, so this is multiplied by 1/5. Changing the x values is a dilation from y. Now let's go over to the y's. So y gets negated first of all. So this is a reflection in the x-axis. This is a dilation factor half from x-axis. Remember, you can write those in either order because it can get multiplied by a half and then get negated, and it will produce this still as well. So you can change the order of them. But this one here has to go last. So we're going to say that it is a translation 2 units up. Alright, so all of these will take this to this. Now, how do I check that? Well, what I've got to do is imagine a function. So y is f of x, and I'm going to do all of these things to f of x. I'm going to imagine this as f of x and do all of these things, and it should produce this. Right, so I'm going to go reflection in the y-axis, that's f of negative x, translation 3 units right, f of negative x take 3, so x take 3 goes on in place of x. Be careful here, a lot of students just write take 3 on there. It's literally replacing x with x take 3. Alrighty, what's next? We've got a dilation factor 1/5 from y, which means that every time we see an x over here, we jam in 5x. Okay, that's how we do a dilation factor 1/5 from y. So it's going to be y equals f of negative 5x take 3. So I see x, replace it with 5x. Then what we're going to do is reflect in the x-axis. That's easy, that's just a negative out the front there. So I'm just going to tack that on here. Dilation factor half from the x-axis, negative 1/2 f of negative 5x take 3. And translation 2 units up, I'm just going to tack that onto the end as well, plus 2. So if I define a function f of x and do all of this stuff to it, it should create my new function. Let's see if it works. Okay, so we'll say that f of x equals square root function, and g of x equals, I can't remember what it was, negative square root, open the brackets for the square root, open the brackets for the numerator, negative, open the brackets, 5x take 3, close the brackets for that, close the brackets for the numerator, divide by 4, close the brackets for the square root, plus 2. Did I get that right? Let's see. Negative 5x take 3 over 4 plus 2. Alright, looks good to me. Alright, so now what I'm going to do is just type this thing here to f of x and just see what happens. So I'm going to say that h of x, a new function, is made by doing negative 1/2 times f of, open my brackets, negative, open my brackets, 5x take 3, close, close, plus 2, bang, got it. Okay, so these transformations work because what happens is when I do these transformations, these ones here, to f of x, I make this blue function h of x, which is exactly the same as this red function g of x. So again, I know my transformations work, and you can check it using any graphing program. You can use Mathematica if you like, although I find typing in functions into Mathematica pretty slow. So that's why I use GeoGebra to do it, is it's just a lot faster. Alright, so there we go. Let's do one last question. Okay, so state a sequence of transformations which takes this to this. Right, so same deal. What we'll do is go y equals 3 sine 4x to, so we're going from this to y equals -4 sine 2x plus 6 take 2. Now you might be thinking, oh, Mr. Miller, I haven't done trig for 7 months. How am I supposed to do this trig now? It actually doesn't matter whether it's trig or whether it's a quadratic or a cubic. We do the exact same process. So what I'm going to do is get these ready to pair. So this is my image and image. Right, so over here I'm going to go y on 3 equals sine of 4x. Over here I'm going to go y dash plus 2 over -4 equals sine of 2x dash plus 6. Alright, we're ready to pair. So I'm going to go y on 3 is equal to y dash plus 2 on -4. Here I've got 4x equals 2x dash plus 6. Alright, now again, decision time. What do I make the subject? Alright, so this stuff done to x equals the image. So that tells me that I need to make x dash the subject so that I can get the transformations. So let's do that. So I'm going to go 4x take 6 on 2 equals x dash, and I can write that as 2x take away 3 equals x dash. So divide by 2, divide by 2. Let's pop that in. Now over here, what I'm going to do is multiply by -4 and subtract 2 is y dash. -4 y on 3 take away 1. Alright, let's list the transformations. So we start with x, it gets multiplied by 2. That is a dilation factor 2 from y axis. This then subtract 3 is a translation 3 units left. Over to y, so we can write the negative sign first. I've been doing that, so I've been doing the reflection first. This time I'm going to do the dilation first, so just to show you that it can be stated in any order. Dilation factor, so what's y being multiplied? It's being multiplied by 4/3, so 4/3 from x-axis, negative sign, reflection in the x-axis, negates y, and this is 1 unit down. Translation 1 unit down. And we're done. Alright, so it's these transformations here. They're my set. They're a set of transformations which take this to this. And again, you can check it out yourself on GeoGebra. I don't want to make this video any longer, okay, than it needs to be. So check it out for yourself on GeoGebra or Mathematica. Graph that, set up your function notation to do these transformations, apply those to this, and you should get this. If you don't, I'm wrong.